Welcome back. This is Concept Development Practice page 26.1 on sound. When we looked at the slinky, we saw that we could push the slinky straight in, and as it kind of shoves back and forth, the wave path can move right along the spring. And that's very similar to these air molecules here in this pipe. You will shove them together. This is called a compression. This is compressed air. And then you have a place of very low frequency of air, or low concentration of air, called a rarefaction. And as the wave is moving in this direction, it will shove and then kind of bounce back and then shove the next molecules together, and it bounces back, and the wave path follows along. So sound waves are longitudinal waves. Transverse waves is, remember, when you flick the spring at a 90-degree angle to the path, and the crest is moving along as it goes. Again, the molecules of the spring stay put. It's just the energy that's transferred as it's going through. So when you're talking about sound, suddenly frequency takes on a different term. The frequency of a sound refers to how frequently vibrations occur. So the high frequency sound is heard at a high pitch. So a high note on a piano has a high pitch, a low note on a piano has a low pitch. That's the same as saying frequency. It's just a term used for sound. So here in this pipe of air, you've got a tone producer, you've got a tuning fork that's producing a tone, and it sets up a sympathetic vibration inside the pipe. So the air kind of shoves along the very same way as the pipe, the sound producer, the oscillator, is actually making it vibrate, and it will vibrate at the same frequency as the tuning fork. Now remember that the frequency is going to equal, the frequency times the wavelength is going to equal the speed of sound, and the speed of sound is always going to be 340 meters per second in air. The denser the medium, say water or steel or whatever, is even going to be faster. So speed of sound would travel faster in a railroad track than it would in the air, or even in the ground than it would in the air. So if you're going to find the wavelength, which is lambda, you would do that with a ruler. So if you were to measure along this paper, you've got about, 2.5 centimeters between those crests. Remember, you would measure from crest to crest, and this is going to be something like this, to where you've got one wavelength coming down and then up again, and you're measuring from the top of one crest to the top of the next as it goes. So the next question is, compared to wavelengths of high-pitched sounds, wavelengths with low-pitched sounds are what? Okay. Now you remember, if the frequency is high, then the wavelength is going to be low. These are opposite of each other. So if you're going to have a low frequency, the wavelength would be longer. They're going to be inverse of each other. All right, so remember then, in air, it takes time for this energy to travel. It doesn't travel instantaneously. It actually has to travel through the medium, through the air, through the water, whatever it's traveling in. Suppose you set your watch by the sound of the noon whistle 3 kilometers away. Compared to the correct time, your watch would be what? All right, if you are setting your watch by the whistle, and the whistle was right when it sounded, is it going to take some time for that sound to reach you? Yes, if it travels in air, it's going to be slowed down by the air, and so your watch would be behind. Now the math is here. Here's the math. You've got velocity times time equals distance. We did this in grade school, I think. Rate, if you remember, rate times time equals distance. If you go 55 miles an hour for 1 hour, you've gone 55 miles. Okay, very standard formula. So if we know that the speed of sound, or the rate of sound, is 340 times what equals a distance of, 3 kilometers away? Well, we want meters per second, so we want 3,000 meters. 1 kilometer is 1,000 meters, so 3,000. Well, if you're solving for t, 3,000 divided by 340 equals 9 seconds. So, sound waves will travel as they're shoving the next guy. Think of it as a big, long line of kids, and one person shoves the next, and then that person shoves the next, and it goes down the line. The energy travels. The people stay put, but the energy travels down the line. The closer they are together, the less time is wasted as one molecule is moving towards the other molecule. If they were to touch each other, then they would move, the energy would move faster. It wouldn't take more time for those molecules to touch because they would already be touching. So the more crowded the molecules are, the faster that they're going to move. The slower, the farther apart they are, the more space in between them, the more time is taken up from one guy moving through space to touch the other guy to give the energy to the next guy. So sound waves travel faster in a medium that is denser. And so what's the densest of the mediums? Solids. So if it were to travel in, say, steel, if you put a hammer to a railroad track, you could hear that 3 miles away easily, but you could not hear a sound of the hammer in air 3 miles away because that energy is dissipated by those air molecules having to go a long distance to reach the next air molecule because they're less dense than in solid. All right, number 7. If the child's natural frequency, now we did this when we did the pendulum the other day, if the natural frequency of the child is once every 4 seconds, for maximum amplitude, so if the guy wants to push her the highest, how often need he push the kid? Okay, you need to push at the natural amplitude. So if I want something to be the highest, if I want to set up a natural oscillation in a pipe with a tuning fork, I want the tuning fork's frequency to be the same as the natural frequency of that pipe. Every length of pipe is a different natural frequency. If you have a very long pipe, you're going to have a low frequency. If you have a very short pipe, you're going to have a short frequency. And if you have an instrument, say like a trombone, where the slide can move and make it long or short, then what's going to happen as it's extended, you're going to get a lower frequency. As it's put in towards the mouthpiece, it's going to be a higher frequency, and so you can kind of go kind of trombone sound. Same thing. If the man in question 7 pushes in the same direction twice as often, okay, so he's not out of sync. He's still in phase, but he's pushing twice as often. So I'm not sure what that means. You have to be in contact with that swinger before you can put energy into her. So if he's pushing and she's on the other side, I'm not sure that it would even make any sense. Okay, so which one do you think is going to happen? So will it or will not it help? I'd say his pushes will not help, will not be effective because what? Every other motion, I suppose if he follows her, maybe that's what it is. He's behind her all the time, so he pushes her when she's towards him, and then as she's going away from him, he follows her and pushes her. He's actually slowing her down because she's trying to move back and he's making her move forward. He's actually going to oppose that. Okay? Kind of weird question. All right, so now we're doing the stuff that we did in lab today. We've got a sympathetic tuning fork. So you've got a tuning fork that you're setting up to vibrate at a certain frequency. And if the natural frequency of the other tuning fork is the same, then as one vibrates, it'll set up sympathetic vibrations in the other. Okay, and then you can kind of touch the first and the second will continue to ring. So let's go back to number 9. Number 9 says the frequency of the tuning fork is 440. That's an A on a piano. It will not be forced into a vibration by a sound of. Okay. Now remember that when we talked about harmonics, a harmonic is anything with a multiple of that vibration. So if it has a natural frequency to ring at 440, then the fundamental would be 440. That's 1 times the wavelength. Twice the wavelength, or the second harmonic, would be 880, etc., third, fourth, fifth. So think of if I set up a vibration at higher than the fundamental, can I make it ring? Can I make the other one ring? It's kind of like the man pushing the girl in swing. He's pushing her when she's back. That makes sense. That helps her. But if he's pushing her frontwards while she's trying to move backwards, he's actually impeding her. And for every push that's helping her, one push is actually stopping her. And so if you push twice as frequently, you're not going to help her at all. All you're going to do is give her a bruise. And it's the same thing with a sympathetic vibration. If I can push once every time that it should ring, I can set up a sympathetic vibration. If I push once for every 2 times it rings, okay, so let's imagine that the girl is swinging away, and instead of pushing her every time she comes to me, I push her every other time. I'm still helping a little bit. I'm not going to get the maximum amplitude, but I will keep her going if I push her every other swing. So if you have a frequency that is half of the fundamental of another, you can set up a sympathetic vibration. So if I have an A440, I can set up a sympathetic vibration if I push at 440. So if I were to say push at 440, it would make the other one ring. If I pushed twice as infrequently, like half as much, every other time it rings, I push a little bit. Well, I'm still helping. But if I push twice as frequently, then it's like pushing the girl on the swing. I help her the first time, and then the second time I hurt her, and those two things cancel each other out. So an 880 would not force another one into a sympathetic vibration because I'm actually canceling it out. I hope that makes sense. Now, the fun part of these little tuning forks is that you can set up beats. So beats are the result of alternate cancellation and reinforcement. So let's say that I have a wavelength, whatever that wavelength is, and if I have a wavelength the same over top where they're both helping each other, then they're going to add together. Okay? If I have a situation where they're both opposed to each other, then they're going to cancel out. And a beat is something like this, where you can hear wah very loud and then kind of silent and then very loud again, where you have a kind of a wah 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 sound where two things are slightly out of tune, they're vibrating at different frequencies, and then that frequency, that the beat of the hertz, is the difference between the two frequencies. We'll see that in just a second. So if you set them up, and let's say they've got a question here, number 11, 2 notes of frequency of 66 and 70 are sounded together. The resulting beat frequency, so not the tone that you're hearing, but the wah, 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 that sound. How frequently are you hearing the beats? Those would be the differences between the two frequencies. So you would take 70, subtract 66, and you'll end up with a beat frequency of 4 hertz. That's really cool because you can very easily mathematically predict that. Last question. The accepted value for the speed of sound in air is 332 meters per second at 0 Celsius, at freezing. The speed of sound in air increases 0.6 meters per second for every 0.6 meters for every Celsius above 0. So warm air is easier for sound to travel because it's denser. Just like that it was denser in steel, it's going to be denser in warm air. Compute the speed of sound at the temperature that the room you are in. Okay, so if the room is at 25 Celsius, that's room temperature, 70 degrees, then it's going to be 25 Celsius. Well, just hold on. Let me go check the temperature in the room. I'll be right back. Okay. The temperature in our room right now is 22 degrees Celsius. Okay. So 22 degrees Celsius times 0.6, right? Times 0.6 is going to be 13.2 degrees Celsius. That has to be added to the 332. So if you take 332 and you add 13, you're going to get that the speed of sound in our room today is 345 meters per second. That's how fast it's traveling. Okay,